right. So once again, welcome to this webinar on building structural analysis models with Speckle. My name is David DeKoning. I'm the head of product for Oasys Structural, and I also am the product director for our contributions to the Speckle open source project. With me today is Janessa Mann. Janessa is our technical lead for our contributions to Speckle, and she leads a team that develops connectors and helps deploy that within ARAP, and as well, because it's open source, makes it available for anyone who uses GSA or uses any of the other tools that Speckle connects to. Janessa is going to go into more details, but very briefly, Speckle is a powerful model management tool that provides interoperability and is open source. And at Oasys and at ARAP, we've been supporting it since 2008, and we're really excited today to share with you how you can use it to improve your work. So I'm going to hand things over to Janessa. Throughout the presentation, I'll be keeping an eye on the meeting chat, so please drop your questions in the chat as we go, and I will bring those into the talk and introduce those questions, either as you ask them or toward the end. So with that, I'll hand it over to Janessa.
Thanks, Dave. You can see me on top of the slides, right?
Yep, looks great.
Cool. Okay. All right. Well, hey guys, thanks for joining. So today we want to share a couple case studies and a couple of example workflows and demos of the different ways that you can leverage Speckle and the Speckle kind of ecosystem to build your structural models. So hopefully we'll show that using tools that are from this ecosystem and built on top of this platform, you'll be able to have workflows that fit into the way that you currently deliver your projects, things that leverage your current processes, and also things that hopefully make your life a lot easier. So, I mean, we put this in the description for the webinar, and it's a bit of kind of like a tongue-in-cheek question. It sounds a bit like a joke, but really, I mean, how many ways can a structural engineer build a finite element model? And ask your colleagues, ask your team, and from our experience, you'll likely get so many different answers. And again, so many different answers for the different softwares that you might use. So within your arsenal of different structural analysis tools, a bunch of different kind of import, export, processing, post-processing type workflows that are linking all sorts of software. And oftentimes these links, they're generally pretty static, and they're generally things that are triggered quite manually. So the burden on the engineer is generally pretty high to be able to adapt to changes that you want to reflect in your analysis. So just even here in some of the software that we see, it's a bit of a tangled web in terms of the connections that do exist or can be made between these input, let's say, generation softwares, geometry kind of softwares, processing softwares, and the structural analysis softwares themselves. So how does kind of Speckle fit into this picture? Well, as Dave said, Speckle is a powerful open data interoperability tool. It serves as the hub to connect a series of different applications that we typically use in AEC. And so the purpose of showing this diagram here is to show all the different connections that currently exist, the integrations that exist between Speckle and between these respective softwares. So Speckle is an open source platform. It's an open source product for the entire kind of industry. It acts as a collaborative, multidisciplinary common data environment. So data that you share between your software can be shared with other software that are already integrated into Speckle. And these integrations exist for all the commonly used AEC tools, including now various structural analysis software. So just to highlight on the right there, in terms of kind of connections to structural software, we now have a connection to Oasys GSA and also to ETABS. And so what this means is that data which is created, processed in, for example, let's say Rhino or Revit or Grasshopper, data that moves through Speckle can also be data that is received into our structural analysis softwares. Similarly, data which is produced by our structural analysis softwares, for example, model data in a GSA model, that can also be extracted and entered into the Speckle ecosystem, into the platform, and made available to the other clients that are already kind of connected. So that means that one could build a workflow which translates data between these different softwares, pushes and pulls changes, and set that as kind of the underlying format for sharing any changes in development of the project going forward. So I've mentioned now that we do have the structural connectors, and these connectors here, they are plugins essentially, or they can be used as plugins into the existing tools. So for Oasys GSA, we have Speckle GSA, the Speckle connector for GSA 10.1, and it's just launched as a separate tool that you can use alongside your typical kind of use of GSA. And similarly for eTabs, set up with also the plugin, using it alongside your use of eTabs as well. And just to note that both of these connectors, they are open source. So what this means is that the development of these connectors is transparent. You can go and take a look at the source code on GitHub, where we are centering all our development, and you can, if you want, contribute as well to the development of these tools. And these tools are available today if you do want to try them. So just one note before moving on to some of the demos. I've been hinting at kind of interoperability of data between these different softwares, and interoperability in this case is kind of sitting on a foundation of a shared object model. So to note, for the Speckle platform, we do have a set of Speckle connectors, and these Speckle connectors, they're able to exchange data because they're situated on a shared structural object model. So that's another kind of feature associated with using Speckle. So if you're interested in learning a bit more about the object representation and the classes that we've used for structural analysis models, go ahead and give Dave and I, a message, an email or something like that, or you can visit some of the Speckle forum posts that exist to take a look at the background as well. But this kind of underlying object model, which links the transfer of data between our structural connectors, is based on, or very heavily based on some building smart kind of research and thinking in terms of how to establish interoperability, which can be built progressively into a standard. So this is something very interesting to check out if you're interested in understanding how we might kind of grow the coverage of the conversion and kind of the interoperability between these softwares going forward. So, I mean, in terms of how Speckle can help structural engineers, hopefully by kind of showing the extent of the connections, you can see that Speckle today does offer a lot of cross-vendor interoperability. So interoperability between the structural analysis software, but also the software that we use for processing and creating geometry, for working with BIM, and these, secondary or not secondary, these other kind of benefits here. Hopefully you'll be able to see them very clearly in the demos. So Speckle also will allow one to have automatic revision tracking of the data as it moves between software. Obviously, with the integrations between the different tools that we typically use, Speckle can really help structural engineers by easing the model building process. And of course, in terms of this data sharing, this is an open kind of data platform. It's easy to share the data that you create with your collaborators. And finally, because we're able to extract and place our data on this shared platform, this open platform, we really are building a foundation for kind of further automation of a structural workflow going forward. So enough about kind of like the context, so some demos. So we have a combination of some recorded demos and some live demos. So this one here is the first one. It's a classic, I think, importing stick geometry to build a structural analysis model, in this case, stick geometry from Rhino. So the workflow really is making use of the Speckle connectors, those integrations, those plugins for Rhino and also Grasshopper. And once this has been this data, this geometry data has been pulled from the software and pushed to the Speckle platform. We're able to then pull that data down and recompose it into the native format for GSA and also for ETABS using the Speckle GSA connector and also the ETABS connector. So we'll do a little recorded demo with the GSA connector. And so ultimately what we are looking at is pulling out centerline geometry as pictured in that bottom left corner there, and generating structural analysis elements, some 1D elements based on that centerline geometry. All right, so as we can see, we've got this lovely twisty tower, courtesy of Reynold Chan, one of the developers at Speckle. And please let me know if this video is loading all right for you guys. So you can see there the geometry. That green geometry was a centerline geometry. Here we're specifying other pieces of structural data. So you'll see that there was properties there and materials as well. So we're creating those structural elements based on the centerline geometry, using that grasshopper connector to send that to Speckle. With Speckle, as I said, sharing your data, being able to visualize that can be quite easy. So we're able to see that on a web platform. And finally here, this GSA connector, we've now pulled that data back down from Speckle. And you can see there, it's pulling it, it's scaling it, and it's converting it. And here we have that twisty tower, some of that centerline geometry. And you'll note that, we did provide some of that additional structural data. So we had the materials and the properties, and those come through as well. Yeah, just the classic kind of simple example of stick geometry to structural analysis element. And let me just move to the next slide. All right. So here's where we're going to attempt a live demo. So let's see how this goes. But this is another kind of, I think, workflow that many of you will be familiar with. And this is importing parametrically generated geometry and model data from Grasshopper. So conceptually, what we're doing is making use again of the connectors that exist, the Speckle kind of plugins that exist for Rhino and Grasshopper, combining that with a parametric script for generating geometry and for specifying the structural properties and loads and materials. We'll be sending that to Speckle, so converting that to our kind of neutral Speckle format. And then we'll be pulling that data back down from Speckle in the Speckle GSA connector. And that Speckle GSA connector will be converting all that into native GSA structural analysis elements. So that this workflow is also possible with the ETABS connector, but we'll focus on a demo with the GSA connector. So as we can see at the bottom there, again, a classic script, and hopefully we'll see the generation of that little space frame model at the bottom there. So bear with me as I just switch screens. Okay. Alrighty. So we've got, in this case, again, this is a lovely script courtesy of our friends at Speckle Systems. So we've got a set of initial kind of components for generating the space truss geometry. So we see that here. So we're taking, a surface, and we're building back from that a truss arrangement. So I don't know, let's see if we can just change this a little bit. Just reduce the length of those elements of those members. And this geometry, this line geometry, this will become the base geometry that we create our 1D elements from. In terms of the creation of materials for structural analysis and also properties, we'll be able to, as an example here, drop down a component for creating, a steel material. Oops, if I could spell. And of course, we have other materials available as well, a concrete, timber, so some default materials there. So we'll leave it here with this steel. So specifying some kind of properties, some names, some things to track kind of the data across the model. In terms of kind of the properties as well, we can specify a profile for this set of elements, a profile. In this case, we could do a rectangular profile, just a 350 by 150 section. That's hollow with a thickness of 15 mil. And of course, to show again, to drop down a couple more components. In terms of the, the different structural profiles that are available, there's a few kind of default ones that are here. And so this set of 137 elements here, this represents kind of the current coverage of the different types of structural analysis elements that can be created and also received with these connectors. So in this case, we've got a rectangular profile. We'll do another rectangular profile. We're building up our property by attaching our material and our profile. And now we're assigning this particular set of properties to our elements, which we've generated, based on these components above. And then, of course, to add a bit of loading, in terms of loads, again, we can apply just a straightforward, in this case, gravity load, and we can apply it to, all the elements. And again, in terms of the different kind of structural analysis building blocks that are available, to come back to this little interface here. As I had mentioned, the interoperability between structural analysis softwares and the rest of Speckle is founded on use of a common object model. And these 137 classes here, these different schema classes represent those object model classes. So again, for loading, in this case, let's say we were going to use a gravity load, but there's other types of, standard and basic loads that are available as well. So in this case, we drop down just a gravity load that applied to all nodes and elements in the model, with kind of a default value of -1 in the Z direction for the load. And so we'll bundle all this data together. So now we've got our elements, which have properties, and properties which have profiles and materials. We've got a load, and now we can send this to Speckle. So in sending, we are converting the data that's been generated with these components, and we're sending this to the Speckle server. So we're sending this online, making it available to this viewer here, but also making it available via API to other softwares. So in this case, obviously, you'll see this is what we've generated, like that. And if we take a look at, some of the components of what we've been able to push up, so we see that gravity load there. So that gravity load, as I'd mentioned, it just, I've just left it as a default in terms of a gravity load applied in the -Z direction. We had created just a load case called a self-weight load case. In terms of some of the geometry here, an element 1D, we can focus a little bit on this maybe and take a look at it. Obviously, just a very straightforward component here, one of the members of the truss. and our baseline obviously coming from the Grasshopper script, the property as we built it up also in the script. In this case, our property, which has the 100 by 100 rectangular profile, and also the steel material that we built up attached. So this data model background kind of built up using a combination of Grasshopper and Grasshopper scripting. So now let's bring this back into GSA. So I'll just open now Speckle GSA and give it a sec there for it to come up. So here we have Speckle GSA, and we're targeting Oasys GSA 10.1, version 10.1. And we'll see now that the stream that we've just sent data to, this particular stream here, Blue Tower, this is a stream that we are able to now pull back down into GSA. So first, I'll open up a new GSA file just to contain this data. And give that a sec. And as I mentioned, you can work with this Speckle GSA connector alongside your use of GSA. So in this case, let's say, our Blue Tower model here, here's an empty, totally empty file, and we'll receive this down. So now we'll see we've pulled this data down from where we've uploaded it on the server. We're scaling it, we're converting it from that format that we were looking at in the web app. And in this case, oh, sorry, one more thing to do. I forgot to set the tolerances on the nodes. So let me start that over again. So should have updated the coincident tolerance of the nodes. I think they just collapsed a little bit too much. So kind of a rerun there. And again, our file. And let's bring up GSA again. And receive our selected stream. And again, we're seeing conversion of the elements from our Speckle format. Not me being stupid this time, but we're not collapsing all the nodes because of an arbitrarily large tolerance. So in this case, we've got our model as generated by our Grasshopper script. We see our sections here. So we had that 100 by 100 and that 350 by 150 section I see. So you can see the 100 by 100 members here and that 350 deep one there. And in this case, we've got our, steel property defined. As I mentioned, we've got our properties defined. So we also do, again, we had applied that self-weight load. So we've got that load case and also that gravity load there. And so in terms of ingredients, I think the only thing that we didn't send through, which I should have added to the script, is go ahead and apply a couple of restraints just to show that this model, as received from Speckle with just those restraints applied, should run out of the box. So there we have it. And in this case, we'll just go to our self-weight case. And there you go. So, very quick kind of example here of specifying or generating your geometry, applying kind of structural data, pulling that in, very little work to do anything to post-process it for analysis. So that's example one, demo one of this one. And we'll try one other demo. So this here, and I'll send versions of these streams in the chat at the end of the presentation if you guys want to kind of inspect a little bit the data as well. So this was our space truss example. And another example again of combining Grasshopper and Rhino. So in this case, let's suppose we've got this model here. We have a few floor plates, we have a core, some columns, and we can make use of kind of the geometry pipeline components and start to pull out the different components that we want to represent in our structural analysis model. In a similar manner kind of thing. In this case, we'll do something with a set of concrete elements. So again, specifying a concrete material from the surfaces representing, from the mesh representing our floor plates. We can extract kind of the perimeter nodes that represent that. So you can see that there, sorry. And so we can do that for the floor plate, but we can also, of course, do that for the core as well, where it intersects with the floor plate. And to make this a little bit bigger again, in this case, we can also apply some restraints. So we'll say that we've got some restraints to represent the foundation at the bottom here. And these are based on the nodes that we've already modeled and added in our Rhino model, and a similar type of thing. So we'll create a property to assign to our column elements. We'll just make this circular section 250 diameter, and we'll also attach that property again to the geometry. So in this case, our baseline geometry coming from our geometry pipeline to represent these particular columns. Our property, this will be a beam type element. We're supplying some releases. So in this case, we'll just say that these are all fixed releases for now. At each end, we'll say that there are no offsets to the members either. And in terms of the local axis, we'll just use a kind of global XY plane axes to describe that member. In terms of the 2D, very similar story. So we're specifying the geometry based on the perimeter nodes that represent the floor plate. We're attaching some properties as well. In this case, it's a 2D element. We'll do a shell, and we'll do a 300 thickness kind of uniform 2D property. And I'll do this as well again. So we're going to bundle up.
We've got a question about sending. Now that you've got to the send component, okay. How fast is the conversion, and is it feasible to keep the send button always working so that whenever the parametric inputs are changed or there's an evolutionary optimization tool, the data goes directly through to Speckle or etabs?
Mm-hmm. So in Grasshopper, there is an automatic send. In the Grasshopper component specifically, there is an automatic send. So you can continuously stream changes. In the GSA connector, I can't speak for the etabs connector. For the GSA connector specifically, though, we don't have a continuous receive kind of mode. So as kind of the engineer, as the user, you're the one who will have to consciously say, receive this particular iteration, this particular iteration. There's no kind of continuous receiving in the GSA connector. But you are able to receive multiple iterations of a stream within your GSA file. So nothing there for continuous, but as a user, you can make kind of a conscious step to pull in the different changes.
Which leads us to the next question in the chat. If more info is added to the GSA file, say more load cases or more restraints, and then the information received from Grasshopper is updated, would the information defined in GSA get lost or only override the info from the stream?
Yeah, so in GSA, the GSA connector will make a conscious effort to take a look at what's already existing in the file. And if there's anything existing, keep that. Or if there's anything something that's already been sent but changed in the data, change that. So it won't overwrite, it will try to merge with what's there.
And we've got one more question about, does the stream have to be set up from the start in the stream and no chance to change the receiver app? I think so. So a stream can be received into any number of receiver apps, and the receiver app can change once you've got a stream in Speckle, a receiver app can receive multiple streams. Or you can a stream can be received into multiple apps. I'm not sure if that's the question. And there's another question: any support for Bentley products? We'll drop a link in later. It's not directly related to the structural models, but we have developed and open sourced a set of MicroStation, Open Roads, Open Rail, and Open Buildings plugins. Yes. And Jeff, we'll get to your question later.
So hopefully you guys can see the columns here, and you can see the perimeter nodes that define the edges of those members that we have. So we'll bring in a new fresh GSA file. The units for the geometry in the Rhino model were a little different this time. So I'm going to change that unit specifically for the geometry, but not for the properties. And we'll see this is, the latest stream that we worked with. And let's see if we can pull this down. All right, so you'll see now we've got our members, we've got our 2D members and 1D members. And if we look at our materials, we've got our user-defined concrete. We've got that, that section there. Again, we've got those 2D properties as well. And we do also, I believe, have a gravity load applied. And we did supply or specify restraints. So we do see them there. So let's give this guy a run out of the box. All right. So we'll come back now, take a look at our model that was generated. So here we have our floor plates, our core, our columns. We've run this with a self-weight load, so we can see, our deflective shape there. And yeah, that's another example of pulling through a set of geometry, adding all the requisite kind of structural analysis input data, and performing the structural analysis right out of the receive from Speckle. And in terms of the amount of data that we're working with, you'll see that for GSA specifically, it works out really nicely to be able to work with members. So sending in terms of 1D and 2D members, for example, and then of course being able to take advantage of the auto meshing that GSA has of members, 2D members. So bringing that in and being able to create a model that's got about 3,000 nodes and 3,000 elements with these 2D elements here was quite quick in terms of the receiving. So, maybe one last thing to share here is that, okay, so we have some results now. What if I want to share the results of this particular run with my collaborators? Well, we could totally do that as well. So we'll just send some nodal results in this case. And we'll say, we'll send just the design representation of the model. So just the members as opposed to individual elements themselves. And we'll give that a bit of a sec. So we're now taking the data from this analyzed file. We're converting it to a neutral format so that we can share it if we want later with other components of the Speckle ecosystem. And it's just now sending it to the server. You'll notice probably it's a little bit slower than when we received, because obviously we're sending a set of results data now as well. So give it a second, then we'll be able to take a look at it again on the server online. And see sending complete. And then we can jump now back here. And we'll see. Sorry, I shouldn't have clicked that. We'll see our model here. We'll see the nodes that were created when we meshed, and we'll see as well the results. So in this case, I think we only had the nodal results. Oops, sorry, I shouldn't have clicked so quickly. But we've got results here as we might expect for displacements, rotations, for our self-weight case, with a reference back to the node that contains that particular result.
So we have a question on this. Are the
yes.
results shared through Speckle because they're part of that shared object model?
They are, yes. In this case, when we're pulling it from GSA, we have included results in the shared object model. Yeah, but that's not any reason why you cannot export the results in the typical way that you do. So the underlying kind of mechanism under the hood does use some of the existing GSA API for doing results export. I'm not sure if that's kind of what you're looking at.
Does ETABS follow the same object model for results?
Yes.
Right.
It does,
so
yeah. With some additions, though, for ETAB specific types of results.
Yeah.
So we've got a shared set of basic results for nodes, 1D, 2D, global, and 3D, and for things in ETABS, for example, like frame results and things like that, things that are assembled on a different kind of grouping, those are ETABS specific classes for defining those results. So maybe I'll just jump back now to the presentation. Oh, sorry. To show one last demo, it's a recorded demo of another kind of classic workflow of pulling in analytical elements from Revit. So you've got your BIM model, you've got some elements there that you want to analyze. And in this case, we're taking advantage of the Speckle connector for Revit, pulling out kind of the default analytical model associated with some framing elements, and using, again, the GSA connector, and if we wanted to, the ETABS connector to pull these into the respective structural analysis softwares. So you might recognize that bottom left corner there, that's just the default structural model for Revit 2021. And on that on that right-hand corner there is the GSA representation of that. So let me play this video now. Again, very little kind of work to do to pull this out. This is just directly selecting the analytical elements that we're looking to use for our analysis. We see that coming through. We see that coming through analytical elements translated into the structural 1D element. And pulling this down, again, using the Speckle GSA client. And we'll see that we've got, in this case, we're not generating members, but we're generating elements. And so we have that with the section properties based on the structural families pulled through. So another kind of example of how kind of quick and hopefully more easy it is to leverage these tools, and using Speckle in this case means that your model generated from Revit that data can also be then sent back, obviously, to the other connectors that exist. So just wanted to close with a couple of case studies, some project examples of where we've used, different ways of building structural models that leverage Speckle. As we just saw, the classic export of analytical elements based on what's already been modeled in Revit. This has been used to success on a set of school projects in the UK. And so in this case, you can see it's a rather large, it's full kind of a building scale structure, and this is able to be pulled through into GSA. Similarly, you can see kind of in this particular project here, a civil project again, also in the UK. The use of Speckle here comes through in the use of a bunch of components. So we're using the Speckle GSA component, but we're also using the Grasshopper components as well, and using the fact that data can be exchanged between these different softwares as kind of a foundation for building data exchange with other applications as well. And again, to note, one other kind of project experience that we found, and this is based on another set of projects, international projects, is that Speckle will play nicely with other tools that you might use as well. So in this particular project, they use Speckle in combination with geometry gym. So they use Speckle specifically for pulling out Rhino and Grasshopper generated data into Revit, and then also into kind of further Grasshopper scripts. But they use geometry gym for pulling that same source of geometry data and structural data into GSA. We have the Speckle GSA connector, but of course, Speckle has a full ecosystem of different connectors. So using all these different tools, they'll play nicely together. And another example here, an extension of that previous workflow is now combining the Speckle connectors that exist for Civil 3D. And hopefully in the future, as Dave hinted, we've just released the connectors for some of the Bentley softwares, pulling in inputs from those software, processing them in Rhino and also in Grasshopper, and then taking that and pushing that into Revit, again, using the existing Revit connectors. So we're kind of daisy chaining these different connectors to pass along our data through a full workflow. And one last example of a high-rise tower in East Asia, again, using Speckle with multiple different softwares for multiple kind of use cases, one for updating Revit elements, and one for updating and maintaining a partnered GSA model. So in this case, this workflow, you can really see that Speckle being used with all the different connectors to its fullest, and using that as the common kind of method for updating data across different applications, across different pieces of the project. So hopefully kind of these case studies and also these demos have demonstrated that, pulling Speckle into your workflow, which is something that is easy to do because it really does kind of fit into the existing tools that we use, provides you benefits in terms of interoperability, in terms of kind of change tracking, improve model building, being able to share your data, and also, again, with the use of this overall ecosystem, building a foundation for being able to perform other automation going forward. And so to leave just with some getting started resources, there's a lot of documentation and tutorials and guides that are available online on the Speckle website. There is a community forum for raising issues and connecting with others who are using Speckle, for making suggestions for new features as well, and also improvements and reporting kind of bugs. And generally, I think the response time on the forum is quite high. And of course, as I've mentioned and Dave has mentioned, this is an open source project. So in terms of the structural connectors specifically, you can visit us on GitHub and see development of the GSA connectors and also the eTab connectors whenever you want. And the GSA connector as well, we do have an installer for it. So if you do have a GSA license, you can visit this release kind of page right now and grab the GSA connector to try it out. So I'll leave it there for questions now, but thanks for attending. And yeah, please let's open up the floor to questions or discussion now.
So great question about, are there any other structural connectors being developed by the community?
I don't believe there are any others that are currently being developed. There's been interest in Tekla and Sophistic, I would say, but I don't know of any other active plans for doing that.
Yeah, we do. I think the only one that I'm aware of, there's a small sort of half connector that we're building for our colleagues in Japan. And in fact, we're working with them on that for a piece of software called Snap that I don't believe is used much outside of the Japanese market. But we're building just a one-way receiver for them, which we're planning to open source as well. So we've got a question, how many other consulting firms have been involved in the development of Speckle? That's a great question. We don't have the exact numbers. We know that WSP is interested in the Netherlands. Royal Haskoning has been involved. A number of architectural firms have contributed or been involved to some degree. So we're hoping obviously to grow that community and share resources to build the tools that we need for all our work. There's a great inspiring example. There's a community called Automotive Grade Linux, and this is a number of car manufacturers that have said, well, we all need an operating system for our cars for the future. But we're not going to differentiate on the file system and the base level. So they're all working together to create a version of Linux that's robust enough for working in cars. And then they all build their own secret sauce on top of that, but they're collaborating on that. And that's very much something we'd love to see. Well, I think we'll wrap it up at that. So I want to say a big thanks to Janessa and a big thanks to all of you for coming and listening. Please don't hesitate to reach out if you have any questions. You can reach us at the emails that Janessa showed on screen, or simply at Oasys with a Y @arab.com if you have